This lesson is for 2.2.4 and focuses on rocket propulsion. The big concept of this lesson is that you will explore the various types of rocket propulsion as well as formulas related to rocket propulsion. So, as we studied in our last lesson, all types of propulsion systems are driven by an engine. We've already talked about the first three, and this lesson will focus on rocketry. So rocket propulsion produces thrust by ejecting stored matter. Rockets can be classified by their propulsion type, so liquid, solid, or electric, as well as other classifications: expendable or reusable, the number of stages a rocket has, the size of the payload, or if they're manned or unmanned rockets. A liquid fuel rocket has fuel mixed with an oxidizer and is then burned. The gases escape out of a nozzle and that generates thrust. A solid fuel rocket is where the fuel is burned to generate gases. Then those gases escape out of the nozzle and generate thrust. Here we have the thrust equation derivation. So this looks like a really complicated formula, but when you look at the smaller parts, it's actually more of a plug and chug kind of formula. So our overall thrust is specified down at the bottom. So basically what this formula is saying, that two forces act together to create rocket thrust, and that's mass ejection and expansion of the gas. First, we have to consider the gases as they change from pressure from PO to PE. The pressure is force area, so the resulting force in the rocket is proportional to the pressure difference multiplied by the nozzle area. So that gives us PE minus PO multiplied by A. The gas is flowing out with a mass flow rate, m, and a velocity, ve. And the momentum of this gas is mve. This force is proportional to the rate of the change in momentum. So this results in a force for mass ejection that's given by d over dt multiplied by mve, which is also equal to dm over dt multiplied by ve, which finally results in mve. So this is our impulse equation derivation. You can see the final equation down at the bottom. Okay, and the thrust force is a function of time. So plotting the thrust as a function of time, you can integrate the values to find the area under the curve. This means that you find the total area under the thrust versus time curve to determine the total impulse. Now, if we were in school, we'd be using LoggerPro to have this integrate function. However, we will be using a simulation. So let's take a look at model rockets. This would be more of what we would be doing if we were in the building and in a traditional classroom. So the stages of a model rocket flight begin with launch. We then have our powered ascent. Then after the rocket engine burns out, we then have a coasting flight. Okay, we then have an ejection charge where we then get a parachute and a hopefully slow descent and then recovery. So let's take a look at how model rocket engines are actually designed. So the engine is an actual device that goes inside of the body of the rocket. So it's like a small canister that gets inserted inside the body tube. Most model rocket engines have a paper casing on the outside. And then on the interior, they have a clay retainer cap, which is also an ejection charge. And then, the ejection charge is underneath, excuse me. And then we have a delay and smoke tracing. So we can also have a non-thrust delay and smoke tracking charge. So all of that can be embedded in the layer underneath the clay retainer cap. There's then a solid propellant inside of there, and then the ceramic nozzle. And then all of this is ignited through an igniter cap, which would go in this small area here. So let's talk about how we identify the size of model rocket engines. This is also referred to as model rocket nomenclature. So we have, every number and letter inside of the naming of a rocket engine means something. So here we're looking at the first number, so that's the total impulse code, so that's newtons per second. We then have the delay time, so how long the delay happens, and then we have the average thrust. If you look at this chart over here, you'll notice that we have labels for the letters, so that is our type. So we have 1/4 A, 1/2 A, and A. These give you the types over here, as well as the impulse, so the amount of thrust that we can have inside of these engines. Obviously, A is the smallest, with E being the largest. And then this giant graph gives you way more detail about model rockets and their performance, and then what engine types and how they perform. Obviously, again, we have A being on the smaller side. There are even some smaller ones included in this graph, and E is the largest. And then this last graph here is a visual demonstration of model rocket engine performance. So previously we had talked about how do we find things inside of a graph using the impulse formula. So this is the type of graph that we would be looking at. So basically it plots thrust and time together. So we can see the point of max thrust and the average thrust, as well as the ejection charge activation point, the delay period, all of those things graphed visually.